All right, thank you. Yeah, so things like fair treatment, you may have been reading about machine learning leads to unfairness. The algorithms are not fair, and these are real issues. And so part of them have to be worked out by thinking about how you gather the data, how you're using the analysis, do you have subgroups that are being preferred or not preferred, and all these issues, which are super important, and hopefully your education has helped you to think about some of those. But one of them that's often missing in that is the notion of fairness is not just that everyone gets equal treatment, okay? It's richer than that. So everyone has their own preferences, right? So if I'm going to a website that's trying to sell me stuff and I don't like red socks and you present me a lot of red socks because everybody's getting shown red socks, well, that's not fair. It's not what I want. So I want systems that actually care about me enough to know what I like and what I prefer. And maybe maybe there's no competition between me and someone else. We can both get what we want, or maybe there is, but we should talk about those issues. So you need some economic perspective, and it's not kind of a traditional thing for a computer scientist or statistician to get, is a little bit of microeconomics. So today you're in for a bit of a treat because we're going to bring in some actual microeconomic concepts. One of the most important ones is called a matching market. And so roughly speaking in economics, in fact I think I have a slide that starts to say these things. It's about kind of who gets what and why. So there's a beautiful book by Alvin Roth, who was a Nobel Prize winner in economics for matching markets. And in microeconomics, there's kind of two broad classes of systems that are designed to make markets effective and get people what they want. One of them is based on matching, the other is based on prices. So prices you're all very familiar with. If you go to a market, prices are set depending on supply and demand. There's all kinds of principles on that. So matching may be a little less familiar, even though it's kind of easier. But the famous example that Alvin Roth got the Nobel Prize for is called the kidney exchange. Kidney exchange. So if you have a defective kidney, that's a problem, but you can still live on only one kidney. Okay? If you don't have two kidneys, if you have two defective kidneys, you're not going to live. All right? So when you start to lose your second kidney, you would maybe like to get a transplant from somebody else. All right? Now, who's going to give you a kidney? Right? Well, a family member is probably willing. Not very many other people are willing to sacrifice a kidney, but a family member might be. Okay, so suppose I'm about ready to lose my second kidney and my brother says, hey, I'll sacrifice, I'll give you one of mine. Great. Big problem, there's something called blood type. Right? His blood type and mine may not be the same, and therefore you put his kidney in mine, it'll get rejected, and neither of us are going to be happy. Okay? So how would you solve that? Well, you might set up a market. And this sounds crass, right? And you don't really want to go paying for kidneys. That sounds like a bad thing to start thinking about, right? So instead what you do, and what Alvin Roth did, is he set up a system where it could be that me and my brother, he's willing to give me one, and there's two other brothers over there. And one of the brothers needs a kidney, and the other brother is willing to give a kidney to that person, right? But we have blood type things. So I hope you know what's going to happen. The blood type match, if there's a match, that person's going to give a kidney to me, and my brother's going to give a kidney to the other one. Okay? So how do you set up a system that really does that? so that everybody's, it really works. And you do this timely, and you have preferences and so on and so forth. So anyway, it works. So I think it's like 800,000 lives a year saved by this algorithm. And it's really interesting. I think that what happens is that once you get a match, you are scheduled in the hospital at the same exact moment. And there's a knife held up by the surgeon on one hospital, and they're talking to the surgeon in the other hospital, and they cut at exactly the same time. Because you don't want them to cut over here, and the other person says, oh, hey, I'm out. So anyway, it's kind of issues you get into. So they're real life. They're consequential. They matter. Some of them involve prices and an exchange in that sense, but some of them just find ways to do matching. And I think you probably all know about doctors in hospital, or people that want to, I guess, what's the term? I'm forgetting. Residents, thank you. Residents in hospitals, they want to go to a hospital. Hospitals want certain kind of residents, so there's a big matching. There's an algorithm, it's called Gale-Shapley, that runs and is very successful for many years. Does anyone know why it's been broken kind of in recent years? The Gale-Shapley algorithm, they had to do something new. You're going to learn about the Gale-Shapley algorithm today, by the way. Two-body problem. Okay, so suppose Fernando wants to go to a certain hospital, his spouse wants to go to a different one. But she's willing to go to this one or vice versa, right? And the hospitals have their own preferences for the two of them. There must be a good way to work that out, right? And there is, but it's complicated. And so again, people get Nobel Prizes for stuff like this in economics. So we want to bring that into our world where we don't even know the preferences, right? Because I'm doing a multi-arm bandit, I don't even know which arm I prefer yet. So I got to have some experience, and then I start to do the matching as part of that. Anyway, that's a really interesting class of problems to work on. Very few people have ever worked on that, but it's kind of the emerging field that's really should be worked on. And so there are a couple of people who worked on this and did a really cool paper, and they happen to be in this room, and they're going to be the other two lecturers today. And I specifically brought them in for a couple of reasons. One is that they're really good lecturers, better than me. Secondly, they're just a little bit older than you, and they were sitting in the same seats you were sitting in just a couple of 3 years ago or something. They were undergrads, and now they're grad students, and they're doing this kind of world-leading research. So some of you are wondering, can I do this? How am I going to participate? And I think by giving you two examples of real people that have done this stuff, I think sets the right tone. Okay, so I just got a couple more slides. You're going to learn about matching markets today, and you've already learned about bandits, and you're going to be putting the two together. That's going to be the big project of today. And so this is just a slide reminding you kind of about what the class has been doing. We've been talking about decision makers. We've mostly been concerned with single decision makers. We had multiple alternatives, both in our FDR case and in our bandits. That was more general than most classes on this kind of stuff. But now we're going to have multiple decision makers, okay? And that's where economics is going to come in, but then we're still going to have a learning system. So how are we going to be able to do that? So exploration and exploitation in markets. There's no books on that. There's hardly any papers on that, but it's very real world. So just really quickly to show a picture, and then you're going to get the details. Remember the bandit situation, I've got the guy up over there has got these three black curves there, which are the reward distributions for the three choices, and the person pulls the arms and starts to learn about the rewards and uses maybe UCB to figure out which arm to select next and blah, 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 blah. Well, there's now also a second participant in this market, the bear. All right, and the bear has distributions which are different. They could have been the same, maybe that's another interesting problem to study, but in this one, we made them be different. And the bear is going to be pulling some arms. So if one of them pulls arm one, the other pulls arm three, fine, they both learn about it. But what if both of them pull the same arm? Okay, so you can now make a mathematical model of what happens here. We think that the interesting economic one is that if you both pick the same one, only one of you gets it. It's like going to a restaurant and both of us want that seat, but only one of us can have it. And the restaurant has some say in that. They have certain kind of clients they want to prefer. Maybe people come a lot to the restaurant, maybe a certain age range or whatever. There's going to be legal issues starting to arise, but they're going to have a preference. We're going to have a preference. That's called a two-way market, where there's two sides of it and you're trying to have interactions between them. And we're still on both sides learning about our preferences. And there's huge numbers of people involved. So each person cannot experience every restaurant, and every restaurant cannot experience every person. So all kinds of new issues. And I hope you sort of see, if you were to work in a company like Amazon or something, this is exactly what you would be working on. Okay, these are the big emerging problems. All right, so that's the picture I want to show, and I think I'm now ready to turn it over to Horia Mania, who's going to do the markets part, and then Lydia Liu, you want to stand up and show who you are. Lydia will be doing the bandits meets markets part. Okay.
What?
Yep. There you go.
Hello, everyone. It's great to be here today and talk to you about our work. So as Mike already mentioned, we're very interested in two-sided markets. And another way of saying that is markets in which we have supply and demand. And in some of such markets, like car manufacturers and buyers of cars, we might not have preferences. Car manufacturers just want to sell cars, and then they're happy when someone buys them. But in other famous examples, both sides of the market have preferences. So for example, medical students want to become residents at various hospitals, and they have some preferences for what hospitals they want to end up at. And similarly, hospitals have preferences over candidates. They prefer certain students more than they prefer other students. Okay? So the question becomes, how can we bring together the students and the hospitals? So here's a simple toy example. Let's say we have 3 hospitals and 3 students. And you can see adjacent to each of them their preference for the other side of the market. And what we're trying to do is find out what's the best way to match the two sides. So this is one possibility. And the question becomes, what's a good match? How should we reason about it? And what's a good algorithm for finding matches? So this is what I'm going to talk to you today about. OK, so first thing in order to talk about this is we should define a matching. So a matching is a set of pairs between hospitals and students. I'm going to use hospitals and students throughout this presentation to describe the two sides of the market. And this matching is a collection of pairs such that each hospital appears only in one pair and each student appears only in one pair. We could have hospitals or students that are not matched. That's allowed. And our goal is to our goal, given a set of preferences among supply and demand, is to determine a matching that is an equilibrium for the market. I haven't told you what an equilibrium is, but you should roughly think of it as a matching where everyone is happy. Okay. So in order to start reasoning about this, it's useful to define what's known as a blocking pair. So a blocking pair between a hospital and a student is the following. It's a pair in which the hospital prefers the student over its current match, and the student prefers the hospital over its current match. So let me quickly draw this. Let's say we have a hospital, and they are matched with some student S prime. And we have a student S, and they are matched with some other hospital H prime. If H prefers S over S prime, and S prefers H over H prime, then we call the pair HS a blocking pair. Okay. Okay, then we can define a stable matching, and it's simply a matching in which this does not happen. We have no blocking pairs. Okay. So here's a question for you. Is this a stable matching? And while you think about it, I'm going to copy the example on the board because we're going to need it in a minute. Any ideas? Is the question clear? Are there? Okay. Well, it turns out that this matching is not a stable matching because the pair H3S2 is a blocking pair. What does that mean? Well, we can see that H3 is matched with S3, but the third hospital prefers the second student, prefers S2. Similarly, the second student, S2, is matched with the second hospital, but they prefer the third hospital. So both H3 and S2 would be happier if they were matched together. So that's why that pair is a blocking pair, and that's why this is not a stable matching. It's very easy to change something and make two parties in this market happier. Okay? It turns out that this is a stable matching. If you check all the possible pairs between hospitals and students, you can see that none of them are blocking, which means that this is a stable matching. Now, a natural question to ask is, can we always find a stable matching? Here we have a problem instance, the one I showed you before, but maybe there's something magical about this problem instance. Maybe that's why we were able to find a stable matching. A natural question is whether we can always do this. And in 1962, Gale and Shapley showed that a natural algorithm, which we will see on the next slide, always finds a stable matching, regardless of the problem instance. So this is a beautiful result. It's a constructive result. They offered an algorithm that always produces a stable matching. So that also shows existence of such a stable matching. Okay. So here is the algorithm. It's also known as the deferred acceptance algorithm. And it works as follows. We initialize M to be an empty matching. So we have no pairs between hospitals and students. Then, while we still have some hospitals H that are unmatched and haven't proposed to every student, while we still have such hospitals, we choose one hospital, H, and then we look in the hospital's list of preferences and choose the top student, S, that did not receive a proposal from that hospital. Okay. And then there are a couple of cases that can happen. The student is currently unmatched with any hospital, and they prefer to be matched with H over being unmatched. It's also possible that they might just prefer to not have a match and not go to the hospital at all. But let's assume they prefer to be matched with H. Then we add the pair HS to the matching M. A different case. The student S prefers H over their current matching H prime. It's the case we had on the board before. Then we're going to replace the pair H prime S from the matching with HS. So we're improving the match of the student. And the third case is simply the student rejects the hospital. They don't like their proposal, either because they're matched to a better hospital for them, or just because they prefer to be unmatched. Okay. So this is the algorithm. And now I would like to do a quick run of the algorithm on this example. So the while loop says, while we still have hospitals that did not propose to a student, we choose a hospital. Let's say H2. We don't have to start in order. And then we look at their top preference, and we make a proposal to that student. So in this example, we're going to propose to the second student. Then we choose a different hospital. We choose H1 and make a proposal to their top preference, student S1. Now, H3 is not matched with anyone. We choose the H3 and make a proposal to their top preference, S1. Now we have a conflict here. The conflict gets resolved by the preferences of the student. The student prefers H1 over H3, so H3 will get rejected by S1. We're in the last case on the slide. Okay. So this proposal will not be successful. H3 then proposes to the second student. It goes in order of their preference. So the third hospital proposes to the second student. Now, again, the conflict here gets resolved by the student. The student prefers the third hospital over the second hospital. So the second hospital loses their match with S2, and the third hospital gets matched with S2. Now finally, we look at the second hospital, which now is unmatched. So according to our while loop, we're not done. We know that we had already proposed to the second student. So now we go to the next option we did not consider before, the third student. So the second hospital proposes to the third student, and they get matched. Okay? And now all the hospitals are matched. So the algorithm ends, and we're done. Okay? So it turns out that this procedure will always produce a stable matching. And we're going to prove that in a minute. Are there questions about the algorithm? OK. So actually, I'm going to leave the algorithm on the board, on the slide, and prove the result on the board. So the claim is the Gale-Shapley algorithm always outputs a stable matching. So let's prove this. The first question, one of the first questions you should ask yourself when you try to understand the performance of an algorithm is to figure out if the algorithm always completes. So are we guaranteed that this algorithm will always complete? So we see we have a while loop, and the condition for that while loop, in the worst case, to exit that while loop, we need to have each hospital make at least one proposal to every student. Okay? So we have a finite number of hospitals and a finite number of students. So the maximum number of proposals that we can have is the number of hospitals times the number of students. So this algorithm will always complete. Now, if we want to find, if we want to show that the output of the algorithm is always a stable matching, what we want to show, according to the definition of a stable matching, what we want to show is that there are no blocking pairs in the output. So let us consider a pair, age S, not in M, where M is the output of the algorithm. So again, M is a matching, so it's a list of pairs. And we want HS to not be in that list. Okay? Any blocking pair must be outside of the matching by definition. So now we're considering such a pair outside of the matching, and we want to show that it cannot be blocking. So we have two cases. Case one, H never proposed to S. So this is one possibility. I claim that if this is the case, age has a better match in M than S. So the hospital, in this case, if they never propose to S, they prefer their match from M over S. Why is this?
Hospitals are proposing in order of preference.
Exactly. Hospitals propose in order of preference. So let's say the hospital is here and they has some preferences. S is somewhere in the middle. And we're saying that the hospital never got to propose to S, which is there. It means that the algorithm completed while the hospital was being matched with somewhere over here to the left. Well, if that's the case, then they prefer this student over the student S. Okay. Okay, so this is one case. Then the only other case is the following. How did I phrase it? Well, okay. It's simply H proposed to S, but for some reason, at the end of the algorithm, H is not matched with S anymore. So again, because HS is not in M, we know that at the end of the algorithm, H is not matched with S anymore. But there was a time when H proposed to S. Then S prefers H over, prefers their match in M over H. Why is that? So I claim if H proposed to S, and then at some later, either at that time S rejected H, or at that a later time S switched to another hospital, then eventually at the end of the algorithm, S ends up with a better hospital than H. Why is that? Did I lose all of you? Okay. So let's look at how conflicts get resolved. So if H proposes to S, and S prefers its current match over, S prefers H to its current matching, then there's a swap. What that swap does is always improves the match for the student. So students always trade up. So since students always trade up, the hospital they would end up with at the end is going to be better than H. So we see that in both cases, this pair HS cannot be blocking. This actually completes the proof of the result, and we have shown that the Gale-Shapley algorithm always outputs a stable matching. Okay. So the proof fits on one slide, and you'll have it in the slide deck. Now, it turns out that for some problem instances, we can have multiple stable matches. There can be a lot of them, and we need to reason about them. What makes a stable match better than another stable match? To do that, we introduce another definition, and I promise this is the last one for the full deterministic, full known preferences case. So we're going to call a pair of a hospital and student valid partners if there exists a stable matching in which H and S get matched. Okay. Then a beautiful result says that the output produced by the algorithm we discussed, the Gale-Shapley algorithm, will always produce a matching in which the proposing side, the hospitals, get their best valid partners, and the passive side, the students, always get their worst valid partners. Okay. So this is a surprising result. In particular, it's surprising because, okay, for each hospital, we have some valid partners. It's not clear that we can find a stable match that maximizes their preferences, maximizes the preferences of all the hospitals simultaneously. But this theorem says that the matching proposed by the Gale-Shapley, outputted by the Gale-Shapley, will maximize the outcome for all hospitals simultaneously. That's surprising. You should think about the proof for yourselves. It's not a lot more complicated than what we discussed here. And one more word I want to say about this result is that in a minute, Lydia will tell you what happens when we don't know the preferences in the market a priori, and the hospitals and the students need to explore to learn their preferences. Then, in that situation, this result does not hold, and moreover, it turns out that the proposing side, the hospitals, will have the worst deal in the worst case. So there will be problem instances when the hospitals will get the worst possible deal when they're uncertain. Whereas here, when they're certain about their preferences, they'll always get the best possible deal. Questions about this? Okay. Well, thank you, and now I'll pass the microphone to Lydia. Thank you.
Hello, it's working. Okay, so yeah, thank you, Haria, for telling us about stable matchings in the case where we know the preferences of all the market participants ahead of time. But now we're going to turn our eyes back to the situation where we don't know this information and we have to learn about our preferences in an online kind of way. But let's start with a recap of what you guys have already been studying in the past couple of weeks about multi-arm bandits, and basically the trade-off between exploitation and exploration when you have uncertainty. So the basic problem, just to recap, you have a single agent, and then you have some arms, say 3 arms here, and each of them has a certain reward distribution. So every time you pull an arm, you get a reward that's drawn independently and identically distributed from that distribution, IID. And then you can pull different arms to explore different arms or exploit the arms that are good. So the rewards in general, we assume that they're Gaussian or have tails that behave like Gaussian. So so they're like regular distributions. And so now to recap, what is regret? Just very quick refresher. We have N to denote the horizon, which is the number of rounds that you can play, and K is the number of arms. And here we denote the reward of arm I at time t with x sub I of t, right? And that's capital letter because that's a stochastic quantity. And the A sub t is the arm that you choose at time t. So that's a sequence of arm choices indexed by the time. And the regret quantity is, as you guys already know, is the difference between 2 terms. The first term is the total expected reward of the best arm. So the best total expected reward when we're maximizing the expected reward over all the arms. And the second term is the reward that you actually obtain from the sequence of actions that you chose. So we want to minimize this difference because we want our action sequence to, in expectation, perform as close as possible to the best arm in hindsight. So any questions about this so far? You guys still remember? Okay, great. So one heuristic you guys have studied in the class is the upper confidence bound algorithm. So you construct, based on the past data you have, you construct confidence intervals around the mean rewards for each arm and pick the arm that has the highest upper confidence bound. So it will incentivize the agent to pick arms that it has not explored a lot in the past. So that's why maybe the confidence interval is large. But it also incentivizes agents to sample arms that just have high UCBs because their mean reward is high. So it turns out that this algorithm has a nice regret guarantee. So suppose arm 1 has the highest mean reward, and so the regret guarantee depends on this quantity called the reward gap, which is the gap between the best arm and all the other arms. So intuitively, if the gap is very small, then you have more difficulty trying to distinguish which is the best arm. And that quantity actually does appear in the regret bound. So in general, we know that the regret of UCB is logarithmic in the number of rounds. And this is very good because your regret is growing only very slowly with the number of horizon. And if you look at what is the average regret, when you divide the regret by the number of rounds, that quantity is going to 0 relatively quickly with the time. So in that sense, I'm not suffering a lot of regret from not choosing the best arm in hindsight. And then there's another term, which is the sum of the inverse gaps, which tells us that if the gap is small, then my regret will be larger in the worst case. So now that we've just recapped quickly this single agent multi-arm bandit, what can happen when we add a competing player? So Mike has already talked about this briefly, but here when we have a competing player, they could in general have different reward distributions even for the same arm. So that's how we denoted it on the right. And if they choose different arms, then sure, they can both get rewards. But if they did not, then Mike also mentioned this at the beginning. So one of the agents might be more preferred than the arm. Or in another sense, you can think of one of the agents as being more skilled at getting that particular reward. And so they win the conflict over the other players. And now this more preferred or more skilled player gets the reward. So just more formally, we're considering a bandits market with players on one side and arms on the other side. And the players get noisy rewards when they pull the arm successfully. And the same arm can have different mean rewards for different players. And if you think about maybe the players as people who are looking for jobs, say, and then the arms are like jobs that are available, maybe you and I might not enjoy the same job as equally. So different arms have different mean rewards for different players. And then the arms have different preferences over the players. So the jobs might prefer job candidate A over B, we don't know. So these preferences can also express the agent's skill levels. Maybe I'm better at job A than someone else, but someone else is better than me at job B, and that kind of thing. So here, for simplicity's sake, let's just say we know the preferences of the arms and focus on the players who don't know their preferences. But in general, we can extend this to where both sides don't know their preferences, but let's just focus on one side not knowing their preferences. And as we said just now, if multiple players pull the same arm, only the most preferred player gets a reward. So any questions about the problem setting so far? Okay. So now here's a question. So in the single agent case, we define regret as the difference between the best arm in hindsight and the actual sequence of rewards that you got. But in a matching market setting, right, in a setting where there are these preference structures, what do you think is the best action in hindsight for like a single player? Anyone wants to hazard a guess? So let's just say there's a unique stable matching. What might seem like a good idea? Let's say you are one of the players, and you think, okay, and everyone. So in hindsight, what would you have done? So would you always choose the arm that has the best reward for you? No. Why do you shake your head?
Because it's the chance that if the other player also always has the same reward and that other players preferred more, you will always come away with 0. And I feel like it's better to come away with something even if it's not the maximum than 0.
Exactly. So that's great. That's the right intuition, right? So I can always expect, if everyone else, including me, knows our preferences, then and we're just playing this game, I can't expect to always do better than my stable match. Because if I'm doing that, that means some other player is doing suboptimally, right? So more likely than not, I'm going to get kicked off from that. So in general, players should always choose their stable match in hindsight, right? So this is the thing I want to compare against, right? Again, we can come up with a notion of regret that's appropriate for this multiplayer problem. And let's go through some notation. But intuitively, it's the difference between the mean reward of my stable match and my actual sequence of matches. So let's denote the stable match as M of I, where I is the index of the player. And then N sub T is the full matching that's played by all the players at time T. So this one tells us everyone what was the arm that they successfully pulled. And mu sub I of j is the mean reward for arm j for player I. And this is sub I because different players can have different rewards for arms. And so the stable regret, like I said, is the difference between mean reward of the stable match and the actual reward of the full matching for player I at time t. So if the stable matching is not unique, then it's less clear what is the best action in hindsight. Kind of depends on how the players might want to coordinate, and it's a bit unclear. So instead of trying to resolve what are the conditions under which that is the best match in hindsight, maybe here we have a way of thinking about these quantities. So we can look at for each agent what is their worst stable match, and we can look at for each agent what is their best stable match, and define two different types of regret relative to those bars. And anything, so we can still say something about these regret quantities, and it will tell us, hey, your regret, the passimal regret guarantee and the optimal stable regret guarantee may tell us different things about the regret. But in any case, it gives us some quantities to compare how well you're doing in hindsight. So if the stable match is unique, then the passimal stable regret and the optimal stable regret are the same, right? And here, optimal just refers to optimal for the players. So if you look at the best, each player has the best valid match. That would be the optimal stable match, and then where each player has the worst valid match, that would be the passimal stable regret notion. Is that part clear? Okay. So let's turn to the algorithmic question now. So what would be an algorithm that can achieve a sequence of matchings that has low stable regret for all the players? Or is this even possible? So it turns out a very simple algorithm can give us some meaningful guarantees. So, but we need to assume there is a matching platform that is able to communicate with all the players. So at every round, the players will rank all their arms by the upper confidence bounds of each arm's mean reward for themselves. So we all look at our own rewards that we have achieved so far, so for the arms that we have pulled, and then make UCBs and rank the arms by UCBs. Then we submit those rankings based on the UCBs to the platform. And the platform now runs Gauss-Shapley using the UCB preferences for the players and the known preferences for the arms, right? And now the players will receive rewards from the matched arms and update their UCBs accordingly. So this is a rather natural combination of two algorithms you guys have learned and know very well. So what can we say about this? Yes? Yeah, so if you run the Gauss-Shapley algorithm, it will always terminate. So at every round, you run it once.
Okay.
Yeah, and then you run like Bandit's algorithm. There's no termination condition, right? You can run it for as long as you want. Yeah.
Often you might have a budget, and if your budget runs out, then that's the termination condition. But,
So here's a theorem, right? If there are n players and k arms, and we run this GS UCB algorithm, then we can guarantee that the passimal stable regret of player I is logarithmic in the horizon. So that's good. That is growing slowly with the horizon. But it's linear in the number of players and number of arms. So if the market size is very big, then possibly this regret is bigger. But there's also an interesting dependence here, which is saying that the regret for player I actually depends square inversely on the minimum gap of all the arms rewards for all the players. So even if that's none of my arms have a very big gap for me, but then if someone else has a small gap, so none of my arms have a small gap, but if someone else's arms have a small gap, then I might have larger regret. So if one player has to explore more, then the cost of that exploration might be borne by other players in the market as well. So why is this the case? We can actually look at this with a very simple concrete example. So let's say there are two players, player 1, player 2. Player 1 prefers arm 1, and player 2 prefers arm 2. But both the arms prefer player 1. So lucky player 1. So this is the stable matching for this problem, and this is a unique stable matching. But now the problem is, in order for player 2 to be matched with their stable arm, player 1 must first decide which arm they prefer, right? Because here, if player 1 is confused between arm 1 and arm 2, so maybe sometimes it chooses arm 2. But when it chooses arm 2, then who will player 2 be matched with? There's only one choice. Arm 1, right? Right. So for player 1 to know which arm is better for player 1, they need to explore 1 over gap squared rounds. And this gap is the gap for player 1. But during these rounds, player 2 will have to pull arm 1. And player 2 will lose the gap its own gap between arm 1 and arm 2. Right, so in the worst case, player 2's regret actually depends on this 1 over player 1's gap squared. And that dependence holds in the worst case. So here you can, in this very simple example, you can see player 2 is like paying for player 1's exploration in some sense. So then also another interesting thing about this result is that Haria told us just now that when we run Gale-Shapley over known preferences, we always achieve the player optimal matching. So it's optimal for the proposing side, right? But I just told you that with preference learning, if we learn preferences with UCB, we can only guarantee the player passimal stable regret, right? And this is not because we didn't manage to prove something about the player optimal matching. It's also true that the player optimal regret can be linear in the worst case, right? So we're not really going to talk about the reason today, but just on a high level is because if some agents have mistaken rankings, it can, so in this particular problem, it can cause people to get arms that are worse than their optimal arm, but they themselves do not correct their mistakes. So this kind of interesting phenomena can happen when one side of the market does not know their preferences. And now if we run Gale-Shapley, we no longer achieve the player optimal matching. So in another sense, this is an interesting phenomenon about how uncertainty affects efficiency and market outcome. So I'll also talk a bit about a simple example just for us to get more intuition as to what's happening. So if you think about a case where all the players have the same ranking over the arms and all the arms have the same ranking over the players. So this is like the case where the preferences are relatively simple. They're just the same for everyone. And player 1 is the most preferred and so on. So in this case, we can actually do a finer analysis that is a bit more fine-grained than the theorem that I showed you just now. And so there's this somewhat complicated expression. But here, just two simple things to note about this expression here, right? So the first thing to note is if there are same number of arms as players, so if n is equal to k, then what is my right-hand side for the worst player? So what is the regret upper bound for the worst player? Same number of arms as agents. So if we don't try to work out the math, let's just think about this intuitively. If I'm the worst player, who is my stable arm? The worst arm. The worst arm. So if I'm doing a Gale-Shapley at every round, the worst player will always get matched to some arm, right? And that arm, can it be worse than the worst arm? No, right? So if you worked out the math, the upper bound is actually 0. So I'll always have negative regret if I'm the worst player in the market, right? Right, and that makes intuitive sense because I can never do worse than who I would have expected to match with when everybody knew them preferences. So I'm only benefiting from the uncertainty, right? I can get lucky and get like a better arm. Yeah. So, but in general, here is just to say that in this particular market structure, now you don't actually see a dependence on the gaps for other players now. So the regret of each player only depends on their own gaps, right? So previously I told you the gaps in when you have arbitrary preferences, it might depend, your regret might depend on the gap faced by another player, but in this global preference setting, it actually doesn't have that dependence anymore, which is kind of nice. So it's only whether you yourself have figured out your preferences. So here now I don't have to pay for the exploration of another player. So we can also run some experiments just so you know that we're not faking this, that you really can have negative regret, right? So if I run this for 20 agents and 20 arms, you can see like the worst ranked agent, which is this faint line here. I'm not sure if you guys can see, but it has this negative logarithmic in n kind of regret, right? So as the horizon increases, the regret is varying very slowly with the horizon. So all the better ranked agents actually have positive log n regret, but the worst ranked agents happen to have negative log n regret, and that's like predicted by the bound we had. So I would also like to talk a little bit about this issue of incentive compatibility. Because when you think about situations where you have an algorithm and you tell humans what to do, a lot of the times humans don't do what you tell them to do. Because they would think about whether this is the best thing for me to do, and I'll try to do that thing instead, right? So here we say that under our algorithm, the players must match with the arm that's assigned by the platform. Maybe that's what the platform does, right? The platform just shows you there's only one Uber you can take, right? They just show you that option, and you can only take that or not, right? It doesn't give you ways to access other options. So now where the players committed to matching with the arm that's assigned by the market, but maybe they can submit preferences that are not their UCB preferences and hope to get something better out of that. So we want to see if that's something they can gain from. So the question now is, how much can a player improve their stable regret if all the other players are playing UCB and then the platform is running Gale-Shapley? And then the answer is maybe by a little bit. So the optimal, we have this lower bound on the optimal stable regret of a player, right? So if the optimal stable regret is negative, that means I'm doing a lot better than my optimal stable arm, right? But then here I'm saying that my no matter how well I do, I can only gain at most a term that's logarithmic in the horizon over my optimal stable arm. So in a case where there's a unique stable matching, it just says that I can't, in the long term, I'm gaining almost nothing above my stable match if I try to deviate from this algorithm, right? And the trick here is, as long as everyone else is playing UCB, then a single player can only do better if other players are making mistakes. So if other players are playing optimally, then this player who wants to deviate cannot do much better than their optimal stable arm. So obviously, open question or interesting question here is, if the stable matching is not unique, then is there any way I can try to game it and get my optimal stable arm, maybe at the cost of other players? And that's an open question. We don't know. So just to show you this plot again, this negative log n bound is achievable, and we can achieve it in the global case, right? You see that some players are actually getting this negative log n dependence. And yeah. So just to summarize, we think that many decision problems today, they're not just about machine learning and collecting a lot of data. There also is a lot of problems that require like some economic thinking and thinking about how the participants in the markets, they're humans. They might be running their own utility maximization, and they have strategic like considerations. And so one of these problems is this matching problem where there is uncertainty in one side's preferences. So today we looked at a multiplayer bandit problem in this setting, right? And we defined this notion of stable regret to account for the fact that there are multiple players. in those markets to get better algorithms. Yeah. Hope that answers your question. Okay. If there are no other questions, I think we might actually end early today. Yeah.
Is Mike back here still, or he wasn't feeling too well? So. Yeah. Okay. So. Any other questions? Otherwise, thank you, Lydia.
Thank you.